Imagine you're working with a floppy spaghetti like polymer chain in solution. No chaperone proteins, no guiding template, yet under the right conditions it snaps into a well-defined shape all on its own. This is the mystery of entropy-driven polymer folding, where randomness paradoxically leads to order, raising the question, can a completely unguided chain self-assemble into complex structures? How can disorder produce order? At first glance, entropy, nature's penchant for chaos, should keep the polymer in a random coil. But when parts of the chain repel water, hydrophobic, and others attract it, hydrophilic, the system's overall entropy increases as the hydrophobic segments collapse together, releasing ordered water molecules back into the bulk. Question: doesn't folding reduce the polymer's entropy? Answer: yes, locally, but the huge gain in water's entropy more than compensates, driving the collapse into a defined conformation. What surprising examples exist? Synthetic polypeptoids, polymer cousins of proteins without any genetic code, have been shown to fold into helix-like shapes purely from side group design. Even simpler, block copolymers with alternating sticky and slippery segments can form micelles, vesicles, or lamellae solely through entropy-driven self-organization, without any molecular blueprint. Why does this matter? If random polymers can reliably fold themselves, we unlock a route to programmable materials. Smart gels that assemble on demand, drug carriers that encapsulate cargo only under specific triggers, or nanorobots that shape-shift in response to environmental cues, all without complex manufacturing or external guidance. What challenges remain? Designing the precise balance of interactions, hydrophobicity, charge, rigidity, so a polymer reliably finds its target fold in a sea of random collisions is non-trivial. And temperature, solvent quality, and chain length can tip the equilibrium toward misfolding or aggregation, mirroring the protein misfolding diseases of biology. What's the big takeaway for curious beginners? Entropy isn't just the enemy of order. In soft matter, it can be the architect. By harnessing the hidden thermodynamic trade-offs between chain flexibility and solvent structure, chemists are teaching dumb polymers to fold themselves into sophisticated shapes, showing that sometimes letting things go random is the surest way to precise organization. Long, flexible polymer chains in solution explore countless conformations, maximizing entropy in their unfolded coil state. Under certain conditions, poor solvent quality or crowding, chains collapse into compact globules to minimize unfavorable interactions. Even though this reduces conformational entropy, this collapse is driven by the gain in solvent entropy or release of bound solvent molecules, outweighing the loss of chain entropy. Carton chains can self-organize into folded states purely through entropic forces, without external templating. Polyen isopropyl-X-rilamide, PN-NiPAM, in water undergoes a coil-to-globule transition above its lower critical solution temperature, folding into compact particles driven by water release, like oil droplets in water merging into larger globules to free up more water molecules to roam, even though the oil molecules lose freedom by clumping. Directed folding uses specific interactions, hydrogen bonds, or programmed sequences to guide a chain into a unique structure, as in proteins, whereas spontaneous entropy-drugged collapse relies solely on nonspecific forces, hydrophobicity, depletion, or excluded volume, to push the polymer into any of many compact conformations. Unlike directed systems that converge on a singular native state, entropy-driven folding yields ensembles of globules with similar radii but varied internal arrangements. Recognizing this distinction clarifies why some polymers form reproducible architectures, while others simply condense. DNA origami uses base pairing instructions to fold uniquely, whereas random polyethylene glycol chains just shrink uniformly when heated, much like assembling furniture from an instruction manual versus crumpling a plastic bag to a small ball without caring about its exact shape. In aqueous solutions, nonpolar polymer segments disrupt water's hydrogen bond network. So, burying hydrophobic groups together releases structured water, increasing solvent entropy. Similarly, adding small crowders induces depletion interactions that push polymer segments closer, minimizing excluded volume. Both effects create an effective attraction between chain segments, driving collapse without direct bonds. These microscopic entropic mechanisms underpin the initial stages of polymer folding, polystyrene in water aggregates above a critical concentration due to hydrophobic collapse of its aromatic backbone, akin to people in a crowded elevator clustering near the center to let more people squeeze in at the edges, increasing overall space. Excluded volume means that any two monomers cannot occupy the same space, so in good solvent, the chain swells to maximize monomer separation. In poor solvent, effective attractions overcome excluded volume repulsion, causing the chain to confine itself to a smaller volume. This confinement reduces the number of accessible conformations, but is compensated by entropic gains in the surrounding medium. The balance of these opposing entropic contributions determines the equilibrium size of the folded polymer. Polyethylene glycol in a water-salt mixture collapses at high salt due to screening of polymer-water interactions and dominance of excluded volume effects, like compressing a spring inside a box. The spring loses its freedom to expand but lets the box's air circulate more freely. Temperature changes affect the balance between polymer-solvent interactions and monomer-monomer attractions. Heating can weaken hydration shells and trigger collapse, while cooling can reverse it. Solvent additives, salts, causal phobicity, shifting the collapse transition point. Thus, by tuning temperature or solvent composition, one controls whether a polymer remains extended or folds into a globule. These parameters define phase boundaries for coil-globule transitions in polymer phase diagrams. P9PM remains hydrated and soluble below 32 dC, but sharply collapses into particles above this temperature in water, much like chocolate that melts in clumps at high temperatures, but solidifies into bars when cooled. The coil-globule transition is often abrupt, with small parameter changes causing large radius reductions, akin to a first-order phase transition. Near the critical point, fluctuations in chain size become large and intermediate states coexist. Once the threshold is crossed, the polymer rapidly expels solvent and compacts. This nonlinear behavior enables switch-like folding responses, useful in stimuli-responsive materials. A block copolymer micelle forms spontaneously when the solution temperature exceeds a narrow window, aggregating dozens of chains, like water boiling. A slight increase above 100 DEC under standard pressure triggers a sudden phase change from liquid to vapor. Entropy drug folding principles guide design of smart drug carriers that encapsulate payloads upon injection, triggered collapse, and release them upon environmental change. Self-healing gels exploit reversible coil-globule transitions to seal damage and restore mechanical integrity. Understanding entropic folding enables creation of responsive hydrogel actuators and sensors, harnessing the inherent spontaneity of polymer collapse without complex chemistry. Thermoresponsive nanogels shrink at body temperature to release embedded drugs in a controlled burst, much like a sponge that shrinks when squeezed, forcing out the stored water at exactly the moment you need it. Predicting entropy-driven folding requires capturing many body interactions, solvent effects, and chain stiffness, making coarse-grained simulations necessary, yet approximate. Polydiversity and chain branching further complicate phase behavior, demanding advanced theoretical frameworks. Experimentally characterizing dynamic, heterogeneous globules at nanoscale resolution remains challenging. Bridging theory and experiment is essential to reliably engineer polymers with tailored folding properties. Molecular dynamics simulations of explicit water and polymer beads approximate coil-globule transitions but often misestimate collapse temperatures, like forecasting crowd movement in a stadium based on individual behaviors. Models capture general flow but miss local jams. Emerging work aims to encode folding behavior into sequence-defined synthetic polymers, mimicking protein folding's precision without requiring specific binding motifs. Integrating responsive monomers that change hydrophobicity on demand could create programmable, shape-shifting materials. Advances in machine learning may predict coil-globule thresholds for novel polymer chemistries. Ultimately, harnessing pure entropy for structure formation opens a new paradigm of minimalist, self-organizing materials. Sequence-controlled polyamides are being designed to undergo predictable folding transitions solely driven by hydrophobic patterning, like writing a simple script that, when run in a computer, produces an elaborate graphic without any user input, structure emerging from minimal code.